Okay, so now we're going to take on an excellence level topic here for Physics 20 with banked corners. So a car going around a banked corner. And what you're seeing in the diagram here is sort of a cross section of it going around this circle. And it's a horizontal circle, as you can see. And you're just looking at the front of the car. It's coming straight out at you. And there's the angle of that kind of banked corner, theta. First thing we always do, let's draw a force diagram. So we have the force of gravity acting downward. I'm just going to change the color here. We have the force of gravity acting straight down. There's our Fg. We know that that's going to push the car into the ground. Ground pushes back up with a normal force, which will be perpendicular to the surface. There's our Fn, perpendicular to the surface. And what we're doing here is we're kind of assuming that there's negligible friction, that there's not much friction here. And because there's negligible friction, we don't include that on the diagram. But we will in fact include the acceleration. Remember which way the acceleration always goes? It goes towards the center. So there is your AC going towards the center of the circle. Notice it's horizontal because it's going around a horizontal circle when it stays at that same height all the way through. Good, so there's our force diagram. And we're going to analyze this using what we call a tail-to-tip analysis. Let me just show you how this works. So if we do, let's say, uniform circular motion, and we know that F net is equal to ma. Now, this analysis, if you're going to do tail to tip, this is what you do. F net is the sum of the two forces. So we have Fn with an arrow on the top plus Fg with an arrow on the top equal to mac with an arrow on the top. So there's our equation. And this actually tells us how to kind of draw the triangle. This one says we're going to add these two together, tail to tip. And then MAC is going to represent the resultant vector. That's actually what it's telling us. This is how we're going to draw the triangle. Good. So let's do that. Yeah, okay, I'm just going to do this on the side here. Just trying to figure out where I wanted to put it. So we start with Fn, and Fn is going this way. Then we're going to add Fg to that. Remember, you add it to the tip. So to the tip of that vector, we now go down. There's our Fg. Now that's adding tail to tip. Now the resultant is MAC, and you can see that AC is going towards the left. And this is your start to finish vector. So from where you started to where you finished, it has to go directly to the left. So therefore, there's our resultant, and the resultant would be MAC. Good. So there's our triangle, but if we want to solve this triangle, we need to know where that angle theta goes in the triangle. And to do that, I'm going to have to actually show you something. So I'm going to just add a page here, if you don't mind. And I'm just going to grab this diagram, make a copy of that. Okay, so I'm just going to put this on this. So, okay, where are you? Okay, not sure where that was going. Okay, that looks good right there. All right, what I'm going to do is I'm going to do a similar kind of a diagram to this. I'll just draw this one on the left. So we actually have a triangle like this. And let's imagine that angle theta happens to be, for example, 20 degrees. Then we have the AC going this way. Then we have the Fn going this way. And what I'm also going to do is I'm going to bring in another triangle. Like that, a shape like that. And let's see what we can do from here. So this is your Fn. All right, let's do a little bit of trigonometry, shall we? Okay, so therefore, we know that the top part of this triangle here would be 70 degrees, adding up to 90, which makes this angle right here equal to 20 degrees, because those two have to add up to 90 degrees. But Fn is perpendicular to the surface. This is important. So this part right here and this part here, they are perpendicular to each other because Fn is perpendicular to the surface, which tells us that this angle here is 70 degrees. And that tells us, therefore, in conclusion, that this angle here at the top of that arrow is 20 degrees. Whew. Now you don't have to do this derivation every single time. You just got to remember the top of that arrow is 20 degrees. So if we go back to the original diagram, I'll just kind of put that on there. So this angle here is theta. And if you kind of relate that to the triangle that I created, that means this angle here relative to the vertical, that is theta. So you just got to remember that it goes at the top of that triangle. That's good enough. You just memorize that. And we're good to go. Now let's finish it up. Okay, so once we finish this, you do not deal with the F net is ma equation anymore. That F net is ma is just to derive the triangle, actually. Now we solve the triangle. Typically, we don't really care much about Fn. We usually know Fg, I'm just going to highlight these. We typically know what Fg is, and we're typically wanting to know about AC. So those are the two that get involved here. That's opposite adjacent, that's tangent. So we end up having that the tangent of theta will be equal to MAC over FG, or MAC over MG. And notice that the m's cancel. And what we're left with, if we cross multiply, is the fact that AC will be equal to G tan theta. And if you want to bring in the AC formula, that would be V squared over R equal to G tan theta, and then you're on your way to solving. Good? So this is excellence level, a little bit harder. What you need to be able to do, key things, is you have to know how to, I'm just going to highlight these things, choose what color I'm going to use. I don't know what color, I'd go brown, I guess. You got to be able to draw this force diagram to start off with. And you don't have to do the derivation of UCM. You can actually go straight to this triangle. Then you want to draw that triangle. And then you want to derive this particular equation from that triangle. And then you're on your way to solve. That's all we're looking for when you're solving these questions. So, good time for you guys to try one. But before we do, I just want to show you that we could also do this for a plane that has banked its wings. Similar analysis. Let me just show you very briefly. We, of course, have the force of gravity trying to pull this plane down to the surface of the Earth. But what's interesting is there's no normal force because it's not actually in contact with the ground, but there's force from the air. And so it turns out that the theory goes that the force from the air lifts the wings, and it's perpendicular to the wings. So therefore we get this lift force. There's your F lift, or F from the air, and it is perpendicular to the wings themselves. And it causes an acceleration towards the center. And can you see that this is pretty much the exact same thing as a banked corner? That's why we call it banked wings. It's just instead of Fn, now we talk about F lift. Good, so now you know how to deal with planes as well. All right, so we're going to take on a velodrome situation, like on a cycling track, but we're going to have this question where there's no need for friction. Okay, so not entirely realistic, but we're going to assume that this bike is going around at the proper speed to stay at this radius and this banking angle with no friction necessary whatsoever. Now, what speed would that cyclists have to go. I recommend you try it yourself first. Just pause. Okay, so let me show you what we're looking for when you're solving these questions. First, we need to draw a force diagram. So I'm going to draw here's the incline related to the question we're seeing here. And we know this angle right here is 40 degrees. You don't have to actually draw a cyclist. Okay, that's a pretty difficult diagram to draw. So I'm just going to do that as a box. Here is the cyclist, looks just like him. And let's draw the forces. So we have, again, force of gravity. There's our Fg. Normal force perpendicular to the surface. And then what I recommend you guys do for AC is to draw the horizontal circle this person's actually traveling along when it's staying at the same height. If you draw that horizontal circle, it makes it so much easier to draw the AC, which goes right towards the center. Good. There's your force diagram. Good. Next thing I have to do is actually draw the triangle. And although you're not required to show this, I'm going to do it anyways. Here's the UCM. There's our FNet equal to MA. And here's our FN plus FG equal to MAC. So we will not require this part, but I find it really helpful to help me draw this diagram. So now we can actually draw the vectors. We have Fn. To the tip of that, you add Fg. And then from start to finish, here's your MAC. Going towards the right, there's your MAC. And remember that 40 degrees is going to go up at the top of that triangle. So here is 40 degrees up at the top. So there's your vector diagram. And finally, now we do the analysis. So again, just a reminder, we know Fg, or we can deal with Fg and MAC. We know nothing about Fn. So we want to deal with these two quantities. So that's going to, let me try a different color here. So now we have the tangent of 40 degrees becomes equal to opposite, MAC, over adjacent, which will come out to be mg. That's your Fg. Masses cancel, so we don't need to know it. And as I've derived before, we have AC is equal to G tan 40 degrees. I'm just going to add a page here. And you can find this if you want to. While we're here, this is going to be equal to 9.81 times the tangent of 40 degrees. So let's do that first. Just going to check my mode. Good. So 9.81 times the tangent of 40. And we get about 8.23 meters per second squared. So now we know what the centripetal acceleration is. But what we're looking for here is the speed v. So now we use AC is equal to v squared over r, and we're solving for v. That will eventually become the square root of AC times r, which is a square root of 8.23 times the radius of curvature, which is 20 meters. And that comes out to be, let's see how many sig digs I gave myself here. Looks like 2 sig digs. So our answer comes out to be 13 meters per second approximately. Good. Okay, so that's one of our most difficult questions in this unit. But again, there are just 3 elements. draw a force diagram, draw the tail to tip diagram, and then solve the triangle. And then you're good. Okay, you know enough to be able to finish all the homework for minimum speed and bank corners. I'll see you in the next lesson.